Hello, my name is Clovis Linkus, Senior Research Scientist at the Florida Solar Energy Center, University of Central Florida. Under funding from the Gulf Coast Hazardous Substance Research Center, we have been studying environmentally acceptable approaches to the treatment and disposal of refinery-based waste streams, particularly that of sulfur. The removal of sulfur from crude petroleum and natural gas is a major process in refinery operation worldwide. The predominant sulfurous waste product of hydrodesulfurization is hydrogen sulfide, H2S, a noxious poisonous gas. Conventional treatment technologies convert the H2S into sulfur and water so that the original energy content is lost. We are developing a UV photolytic process that decomposes H2S not only into sulfur, but hydrogen gas as well. The following is a video showing how the process works. Let's take a tour around the sulfide loop showing how H2S is photolytically converted to its constituent elements. Much of the apparatus is located inside a fume hood, mainly for safety reasons. The H2S supply, the scrubbing apparatus, and associated plumbing are shown. The photoreactor and circulation pump are off on the right, gas chromatographic apparatus is off on the left. This is our hydrodesulfurization plant, consisting of a tank of hydrogen sulfide with a regulator. The yellow object in the lower right is an H2S sensor. The sensor is electrochemistry based and gives off an intermittent beep at 10 part per million and continuous above 20 part per million. The darker object in the middle toward the rear of the area shown is the H2S flow controller. In order to use only as much H2S as is necessary to balance the chemical turnover in the photoreactor, this flow controller is coupled to the pH in the scrubber vessel. We have also installed a flow monitor and integrator into the H2S supply line so that we can quantitate the amount of H2S flowing into the system. A check valve in the upper right prevents scrubber solution from backing up into the monitor. Our scrubber vessel consists of a glass round bottom flask fitted with multiple ports to accommodate H2S inflow, scrubber solution outflow, and sulfide solution returning from the photoreactor. It also has ports for a pH monitoring electrode and a pressure relief valve. Initially, the vessel contents, consisting only of scrubbed bisulfide ion, are clear in color. This is the pH monitor, which tells the H2S solenoid when to supply more gas to the scrubber. In this scene, the monitor has been set to pH 7. By maintaining scrubber pH in the neutral to moderately alkaline range, sulfur-laden solution coming from the photoreactor can be induced to release its sulfur content. Once the system is brought up and the photoreactor turned on, the photolight quickly turns yellow from the production of complex sulfur. Even though most of the disulfide complex decomposes in the scrubber, enough remains so that the scrubber solution in the steady state is decidedly yellow. Shown here is a flow meter and a pump that draws sulfide solution from the scrubber and sends it to the photoreactor. The UV photoreactor is housed in a 6-foot black box standing on the floor to the right. The photoreactor consists of a 30-inch, 60-watt low-pressure mercury lamp mounted along the center line of an annular quartz reaction chamber. This is a rare view of the photoreactor opened up while in operation. A steady flow of hydrogen gas bubbles can be seen rising to the top of the reactor. It was difficult to operate the gas collection apparatus straight out from the headspace of the photoreactor, so we installed a small gas separation vessel just downstream from the photoreactor. In order to be able to measure the gas evolution volumetrically, it was necessary to maintain a constant headspace inside the separator. To perform this function, a fluid level gauge was connected via a relay to a small pump. In this view, the photoreactor input, output to the scrubber, gauge wiring, and ancillary circulating pump can be seen. Segregated pockets of gas and sulfide solution can be seen pushing through the 1/4-inch connection tubing into the separator. The gas exiting from the separator passes through a sampling loop on the chromatograph and then on to an inverted graduated cylinder, whose liquid volume is displaced by the hydrogen gas. Once the hydrogen gas has been separated out, the complexed sulfur solution is returned to the scrubber. The scrubber vessel immediately becomes turbid from the release of elemental sulfur, as it is being held at a pH where the disulfide complex is unstable. This is how the scrubber vessel appears in the steady state. To collect the sulfur precipitate, a dual inline filter arrangement has been installed between the scrubber vessel and the main circulating pump feeding the photoreactor. Stopcocks above and below the filters can be opened or closed so as to direct the scrubber effluent through either or both of the filters. This feature enables the operator to remove and clean one of the filters while the system is still running. Here the operator demonstrates how a filter can be taken offline while the system is operating and continue collecting the sulfur through the other branch. The sulfur is typically dried and weighed to confirm the mass balance of the overall system. The collected gas has been shown to be mostly hydrogen, but it is of interest to know how much H2S is co-evolved and correlated to the operating parameters of the system. With the aid of a multi-channel sampling loop, fixed volume samples, typically 1 milliliter, of the gaseous output from the system can be sent through the chromatograph. Separation of the gases in the HACEP dB packed column under helium flow is easily accomplished. The output from the thermal conductivity detector is shown on the screen. In this case, only a single peak, whose retention time corresponds to hydrogen, is shown. In conclusion, we have demonstrated a closed-cycle hydrogen sulfide treatment process that decomposes H2S via UV photolysis into its constituent elements, sulfur and hydrogen. One not only recovers marketable sulfur, but also hydrogen gas that either could be sold on the commodities market, burned to produce clean process heat, or recycled back to the desulfurization plant. This process may someday help oil refineries reduce their increasing reliance on outside sources of hydrogen and make sour gas refineries more profitable. Thank you for your attention.